Hello everyone, this is Shoujie. Today I'm going to present a paper, Pairwise Document Similarity in Large Collections with the MapReduce. It is published by Tamer, Jimmy, and Douglas. Here's the agenda. I have introduction, MapReduce framework, pairwise similarity for both small collection and large collection, and the experimental evaluation, including scalability and complexity. So introduction, this paper is mainly about computing pairwise similarity on large document collection by MapReduce. So as we know, the computing pairwise similarity is widely used, such as PubMed, which is a life science literature platform. So they have a function named more like this. You can find more similar papers. As well as Google Scholar, it also have a similar function. When you search a paper, on the paper, you will find related articles. If you click that one, you will find more similar papers. So the history of the MapReduce, it is firstly bring up by two computer scientists who work in Google. One is Jeffrey, the other one is Sanjay. The main framework of MapReduce, it includes two parts. One is map, the second one is reduce. So the map is applied to every input key value pairs to generate an arbitrary number of intermediate key value pairs. While the reducer is applied to all the values associated with the same intermediate key to generate output key value pairs. So back to the pairwise document similarities. The original similarity comparison between two core documents will be based on, this formula. And basically it is going to calculate the shared term, the weights, and sum them together to finally get to the similarity between two documents. However, this type of method, it is quite time consuming and also it's not efficient enough for large size collection. So that's why the author tried to explore the MapReduce methods to do the pairwise similarity in large collection. So within this methodology, and it's split into two main parts. The first one is indexing. The second one is the pairwise similarity. So here is an example with three different documents. Each one has different terms. So the first step is to list each unique terms from each document. So for example, document 1, it has ABC three terms. And for each of them, you will label the document as well as the number of the term. After that, you will do a shuffle. Basically, you will combine them by unique term. So for example, A, it has two terms, two A's from the document 1 and 1 from the document 3. And there's a similar, procedures for the other terms. So this basically is the indexing step. After that, you will do a pairwise similarity analysis. So you will look into each term. If the term only have one document, so which means it's only unique to that document. It doesn't have any like pairwise, other documents to compare with. So it will stop for the further analysis. But if the term has more than two documents, it will, match together and also calculate the number of the match. So for example, so for turn A, it has two matches between, document 1 and 3. Similar things to the turn B. After that, they will do another shuffle, and based on different combination of documents, for each document, document combinations, it also lists, the number. And then we'll follow by reducing and calculate the final similarity score between, in each combination of documents. So from the result, we could see between document 1 and 2, there is only one match, while 1 and 3, there are 4, and which indicate the 1 and 3 are the most similar combination of, documents. Based on the methodology, they apply to a real data set, which is a quant 2. And it is a collection of, around 900 K documents. And the size is around 2.5 gigabytes. They use Hadoop software to implement MapReduce. And the device, they based on 20 machines. Each machine had 2 single core processors. Another unique step is the depth cut. They remove top 1% of most frequently used term. So after those conditions, set up the conditions, they mainly look into scalability and particularly analyze the correlation between the computation time and also the collection size. So from the result, it indicates they have very linear correlation between the time and also the size. If you look into the plot, if you only have 10% of the collection size, and the time takes around like 20 minutes, while if you have the entire data sets, that it will cost around like 2 hours to finish the computation. So besides that, they also look into the number of intermediate pairs, which is the largest part to take the computer space. So previously we mentioned they try to remove 1% of most frequent terms, and it will and here they try to compare, remove 1% without, remove. And there are significant difference on the, the number of the intermediate pairs. So if you remove the 1% of most frequent terms, the number of intermediate pairs is only 3.7 billions, while if you don't, the number will be 8.1 trillions. It's a huge difference. Besides that, they also look into the correlation between the number of pair and the size. Theoretically, because this is a pairwise analysis, and the correlation would be non-linear, and it's n square, correlation. However, it's very surprising to see, if the depth cut is 1%, so it is quite a linear correlation. Similar phenotype behavior happened on the cutoff, depth cutoff at 0.1%. the smaller cutoff it is, and the closer, you know, the curve would be to the standard, to the original curve. So basically from, you know, the paper, there are two main conclusions. The first, pairwise similarity computations for large collections can be efficiently implemented with MapReduce. And also removing high frequency terms result in approximately linear growth in required disk space and running times with increasing collection size. The last one is the list of reference. So if you have any questions, you can DM me on the Slack. Thank you so much.